Okay, so this is the first review sheet for the second semester exam, and this is actually going to cover some topics that were covered during first semester. So I just wanted you to have one more look at a few topics that we talked about in first semester. So let me see if I can help you out with this review sheet. So number one is all the way back to chapter 1. We have this line called A that passes through these 2 points. Another line B passes through this point, and we know that it's perpendicular to A. So what's the equation for line B? And we're supposed to write the equation in slope-intercept form. So this is testing your ability to recognize that two lines that are perpendicular to each other have opposite reciprocal slopes. They're opposite reciprocal. So I need to find out what the slope of this line called A is, and I've got a formula for that. y2 minus y1 over x2 minus x1. So the slope for line A is 4 over 2, which is 2. So that means this line called B has a slope of the opposite reciprocal of 2, which would be negative, that's the opposite, 1/2. That's the reciprocal. Okay, so I take this point that line B goes through, this is my x and this is y, of course, and basically I'm going to plug x, y, and m into slope-intercept form. Y equals mx plus b. So y is 3, m is negative 1/2, x is negative 1, and I'm going to solve for b, and once I have b, I already know what m is, I can write the final equation for this line b. So 3 is equal to 1/2 plus b, and if I subtract 1/2 from both sides, I get 2.5, or in fraction form, that's 5/2 equals b. So my final answer will be, for this line called b, is y equals negative 1/2 x plus 5/2. And that is your answer for number 1. All right, so for number 2, we have this tour group that is split up into 2 groups waiting at a fast food restaurant. The first group bought 6 slices of pizza and 5 soft drinks. Second group bought 5 slices and 5 drinks. For that amount, how much does 1 slice of pizza cost? So I'm going to set up 2 variables because this is going to be a system of 2 linear equations. So I'm going to let x represent 1 slice of pizza, the cost. And I'm going to let y represent the cost of a soft drink, because we're given these amounts that were paid as a group, a total of 6 slices of pizza and 5 soft drinks. So we're going to break it down and find out how much does each cost, 1 slice and 1 soft drink. Okay, so knowing this, that these are my variables, I'm going to write a system. So the system that represents the first group and what they bought would be 6 slices, so 6 times x, and then 5 soft drinks, so 5 times y, and that totaled $28.93. And then for the second group, 5 slices of pizza, so 5 times x, plus 5 soft drinks, 5 times y, and that equaled $25.50. Okay, so the easiest way to do this, solve this system, you have options. You can use substitution or elimination. You have other options as well, but probably the easiest option is just to use elimination because you have matching y terms that would cancel if you subtract. So I'm just going to subtract all these like terms. So 6x minus 5x is 1x. The y's will cancel. And then when I do 2893 minus 2550, that's 343. And all this asks me to do is find out the cost of one slice of pizza. I don't have to solve for y in this case. Typically, when we solve a system, we solve for x and y, but that's not really necessary here. So my final answer is one slice cost $3.43. And that's your answer for number 2. All right, so for number 3, this is a system in 3 equations, 3 variables. Okay, so we're supposed to find these 3 numbers, find the numbers using a system of 3 equations. Well, if I'm going to have 3 equations, that means I'm going to have 3 variables. So x is going to represent the first number, y will be the second number, z is going to be the third. And then I just read through these sentences and they represent equations. So the sum of 3 numbers is 6. So these 3 numbers added together equal 6. Okay, so here's another equation. The third number, which is z, that means equals, the sum of the first and the second. Z is the first and the second numbers added together. Now here's my final equation. The first number, which is x, that's equals 1 more than the third. So I take the third and I add 1 to it. And so here's my system. And again, you have some options. You can do elimination. If you do elimination, then you're going to have to rearrange these equations so that the like terms are matched up vertically. You could also do substitution because you know that, for example, x is z plus 1, so you can replace z plus 1, these x's with z plus 1. So let's just go with substitution. That's the way I'm going to choose to do this. So I'm going to let these x's be replaced with z plus 1. Okay, so in the middle equation, when I replace x with z plus 1, I get z equals z plus 1 plus y. And then continuing to solve, you notice that the z's would actually cancel each other. If I subtract z from both sides, I get 0 equals 1 plus y. So actually I've solved for y here. Y is -1. That's my second number. So now I can go up here. Not only can I replace I can replace x with z plus 1. I can also replace y with -1, because now I know what y is. Okay, so 1 plus -1 is 0, so I get z plus z, that's 2z, which equals 6. So that means my third number is actually going to be 3. So now all I have to do, I can choose any of these equations where I've already found one or more variables. I need to find x, so I could actually use either the first equation or I could use the bottom equation, probably the 2 easiest ways to go. I think the bottom equation is probably easier because all I have to do is replace z with 3 and I get x. 3 plus 1 is 4. Okay, and then you should double check. A solution should make each one of these true. So if these are actually solutions, then I should test and make sure that not only one of them is right, not just 2 of the 3, but all 3 have to work with these values. So let's see, if I let x be 4 plus -1, that's 3 plus 3 is 6. Okay, that checks. Here 3 is equal to 4 plus negative 1. That checks out. And then here, 4 is equal to 3 plus 1. Okay, so I'm feeling good. And so my final answer, I can just leave it like this. I've identified each of the numbers in variable form, and then I've written underneath what each of the numbers actually equal. All right. Right, now we're into Chapter 2 material, and this is called a piecewise defined function. So let's sketch the graph of this. It's really one function, but it's going to be in 3 separate pieces. So this first piece, this would be the equation y equals 8. So if I go up to, that's a horizontal line that passes through the y-axis. It crosses the y-axis at 8. 1, 2, 3, 4, 5, 6, 7, 8. That's right here near the top. But according to this, I'm only showing the line where the x-coordinates on that line are less than or equal to negative 1. Okay, so here is where x is negative 1 on that line. And I'm only showing the line where the x values get lower, less than negative 1. So I'm going to include negative 1. So I'm going to shade in, make a solid circle, and then I'm going to have a line, basically it's a ray, that only goes in this direction. So that's the piece y equals 8, only for x's that are less than or equal to negative 1. Okay, now we'll do the line y equals 2x. And so y equals 2x plus 0. Notice the b is 0, so that means I'm crossing through the origin. I've got a slope of 2 up to right 1, up to right 1. But notice it's only for x values on this line where it goes from negative 1, which would be right there on that line. That's where x is negative 1. And it stops for the x values that are 4. 1, 2, 3, 4. So I need to go right there, and that's as far as that segment goes. So notice I've drawn I put dots on the line, but I'm not going any further for this line than where x is negative 1, which is right there, and where x is positive 4, which is right here. And actually, you notice that it doesn't say or equal to for either, so that means I'm going to have open circles for both negative 1 and 4. That just shows that they're actually not going to be part of the line, and I'm just going to do my best to do a line segment to connect those two. So open circles on the ends, and then you just shade everything in between. This is a between statement. X is between negative 1 and positive 4. And then finally, here's the line y equals negative 4 minus x. So the y-intercept is negative 4. So this line has a y-intercept of negative 4, which would be right here, and a slope of negative 1. So you can think about starting at negative 4, and then if you went down, you would go right, down and right, 1, down 1, right 1. And this one's only for x values that are greater than or equal to 4. So I really haven't even gotten there yet. I'm still doing down 1, right 1. But right here at this point is where the x value on that line is equal to 4. All right, and it's going to be going greater than 4, and it's also going to include 4. So this is going to be a solid circle, and then I'm just going to show that this is a ray that's going to continue on in this direction. So actually these little dots that I've made to just give me an idea of what the line looked like are not needed at all. And so there is the piece that is defined by that final equation, and then this is called the domain restriction. Now I'm supposed to do the domain and range, and this will wrap it up. So the domain looks like, and when you're trying to determine domain, look at all of your pieces and see how much of the x-axis would be covered. Well, it's covered from -1 to -infinity with that top piece. The red picks up there and goes to 4, and then the final piece starts at 4 and goes forever to positive infinity. So we have the entire x-axis covered. And I'm going to use interval notation. This is a way of saying all real numbers. You could also just do it as domain. This is called set builder notation. All x's such that you have all real numbers. And then the range, now you're looking for the y-axis coverage. And for the y-axis, it is covered from -2 all the way up to 8. We don't include -2, but we will include 8. So for the range, we will say it's from -2 to +8. And I'm going to do this using interval notation and set builder. So with interval notation, we would say it like this: -2 is not included, notice the open circle, but 8 would be included because we have this closed circle. And the way we show that 8 is included is with a bracket. So the parentheses means that it's not included, the bracket means that it is. And using set builder notation, you would just, well, let me go ahead and finish the rest of this. We also have this final area that is down here at 1, 2, 3, 4, 5, 6, 7, 8, -8. So it's getting less than -8. So the way we show that in interval notation is from -infinity, which is never included, to -8. And since that's a solid, it would be included. So once again, using the set builder notation, the range, that involves the y's, such that we would say from -2 to 8, and then we would include also all of the y's that are less than or equal to -8. Okay, that takes care of number 4. Number 5 is another piecewise defined function that we are given. We're given the graph. We have to come up with the function itself. So we'll just call this f of x. And now let's see if we can define the 3 pieces. So I'll just call this one number 1. This is piece number 2. And there's number 3. Okay, so these are linear equations that are restricted by with their domain. So let's see, this is a line. Let's see if we can tell where the y-intercept is going to be. So looks like to get from one point to the next, we go up to, right to, up to, right to. That puts me right there. It's another way of saying a slope of 1. So this line, this piece has a y-intercept of 4, and it has a slope of 1. 2 over 2 is equal to 1. So here's my y already given. F of x is the same thing as y. Y equals 1x plus 4. Okay, now it's not the whole line though. Okay, if I stop there, then that would be saying it goes forever and ever in both directions, but it doesn't. It starts where x is -2, and it keeps going less than that. So I'm going to restrict the domain by saying it is this line, but only if x is less than -2. And it's not including -2 because of the open circle. All right, now let's do piece number 2. This is the horizontal line y equals -3, but only for these x's that are between -2 and +3. And notice we have closed circles, solid circles, so that means we're going to say or equal to. So that's piece number 2. All right, so for piece number 3, Let's keep on working our way up until we can see what the y-intercept is going to be. So let's see, the slope looks like it's up to left 1, up to left 1. So let's just keep on doing that. Up to left 1, up to left 1, up to left 1. Okay, so let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here I went, remember, up to left 1, so that must be 12. All right, so I know the y-intercept is 12, and we were doing up to left 1. That means negative 2 is the slope, negative 2x plus 12. But it's not the whole line, it's only for x values that start at 3 and get bigger. And we're not going to actually include 3, so we're going to just leave that as greater than. Okay, so for number 6, we have this graph, and we are supposed to, first of all, determine the end behavior of the graph, and then we're going to identify any relative maxima or minima. So the end behavior would look like this, describing the right end as x approaches positive infinity. That's going to the right. The graph, which is identified in this case, we can just say y, or if you did f of x, that would be okay. I'm just going to use y since that's what's on the graph. Since it's going up, we can say that y is also approaching positive infinity. So that describes the right end. And then as x approaches negative infinity, that's as we move to the left, the graph is going up on this end as well. So it's going up in both cases. So that's the end behavior. And then as far as maxima, minimum, these are referred to turning points. So I've got 2 relative minima right there, and it looks like I've got 1 relative maximum. And so you can state relative minima in this way. I'm going to say, you can say it one of 2 ways. You can say that it's between -1 and -2, x equals -1 and -2. So let's say this. We have relative minima. One of them is between x equals -2 and x equals -1. And if you can tell it's closer to one versus the other, it would be okay if you say near. In this case, x is near -2. I wouldn't count that wrong either. Okay, and then we have the other one over here. This is between x equals 1 and x equals 2. And then we have this relative maximum. The relative maximum is a turning point that goes from up to down, and then minima from down to up. So this looks like it's between 0 and 1. And that takes care of number 6. Okay, number 7, we jump into chapter 3. You're not going to be asked to change this into vertex form, but I'll go ahead and show you how to do that. Pretty easy, not too bad. If you remember how we complete the square, you, in these parentheses that I've made, think about the completing the square process. We would do x plus, and then we always divide whatever's in front of x by 2. All right, so x plus 2 squared. Now if you just take this number squared, 2 squared is 4, and just pretend like you're going to come up and subtract it off the end of the standard form, and then put those 2 numbers together, and you get -7, and that's called vertex form. And the reason why we call it vertex form is because we can actually see the vertex in the equation. The vertex is -2, -7. So I'll just go ahead and say my answer for letter A. You won't have to do this on the exam, but it's good to know for those of you who are going to pre-cal. This is something that you do quite a bit. The reason why it's so great is identifying the equation for the AOS. If you're dealing with standard form, then we do the AOS as the opposite of b over 2a, and that would be, in this case, the opposite of 4 over 2 times 1. So that's x equals -2 would be the answer. Well, that's also the x-coordinate of the vertex. Notice that? So when we change this to vertex form, we know the answer to this AOS already. We don't have to go through this formula process. So the vertex, that's my answer for letter C, would be -2, -7. Letter D is there going to be a maximum or a minimum value, and then what is that value? Well, the parabola is going to open up, so that means the vertex is at the bottom of the parabola, so I'm going to have a minimum. And the value of the minimum is whatever the y-coordinate is of the vertex, so that's -7. The discriminant, the way we find the discriminant is just this part of the quadratic formula, b squared minus 4ac. So looking at the standard form, b is 4, so b squared is 16, minus 4 times 1 times -3, that's going to be -12. So the discriminant is 28, and the meaning of the discriminant, since it's positive, that means that I'm going to have two real number solutions or roots, which, as far as the graph is concerned, means I'm going to have two x-intercepts. In other words, I should be, when I'm done, I should be crossing the x-axis at two different places. Okay, and then we're going to find out exactly where. So letter F is find the x and y intercepts. So let's do the y-intercept first. That's pretty simple when you're looking at standard form. That's the one big advantage of standard form versus vertex form, is this y-intercept is easy to spot. It's just that constant on the end. So the y-intercept is -3. As far as the x-intercepts, we're going to have to solve this equation. So pretend like you're solving the equation, the quadratic equation, x squared plus 4x minus 3 equals 0. So what are your choices for solving this equation? Well, you could potentially factor, maybe, but unfortunately this does not factor. There are no factors of -3 that add up to 4. So we'll resort to the quadratic formula, or you could complete the square. So quadratic formula, since we've already found the discriminant, that's part of the quadratic formula, we might as well go ahead and do the rest. So quadratic formula says the opposite of b is -4 plus minus the square root of 28 all over 2 times a, that's 2. And so now you'll go to your calculator and find the decimal equivalent for the square root of 28. So I'm going to grab my calculator. So we do -4 plus the square root of 28. Just plug that into your calculator. And I just hit equals, and then I'm going to divide that by 2. That's what this says. So we're really going to get two numbers out of this, one for the addition and then one for the subtraction. So when I divide by 2, I get 0.64575. I'm just going to say that's 0.65. And now let's see what we get with the subtraction. So if you want to clear your calculator, now you're going to do -4 minus the square root of 28. And then divide that by 2. And that's -4.65. Okay, so when we do our graph in just a minute, we'll see if those look reasonable. And actually, we're at the point now where, well, we got to do the domain and range, and then we'll sketch the graph. Let's just go ahead and sketch the graph, and that might make it a little bit easier to see what the domain and range are. All right, so vertex is -2, -7. All right, so that's right there. Let's see, we have symmetry, so I'll just go ahead and draw this little dotted line to represent where I have symmetry. So that makes it easy when I'm plotting points. If I plot a point on one side of the line, then I just match it up on the other side of this dotted line. Let's see, what else do we know? We know the y-intercept is -3, so once again, that's a point on the line. I'm crossing the y-axis at -3, so that means because of symmetry, I can make another point over here. And then let's just go ahead and do a rough sketch and see what this looks like. So draw this. And I tried my best to hit the points. It's not exactly right. But we said earlier that we're supposed to be crossing the x-axis at these 2 points. Well, I missed the point there. You can see that 0.65, which is just a little bit to the right of a half, it's really where this should go. So that looks reasonable. It's kind of hard to hit my points with this board. And then the other point I should be crossing on the x-axis is -4.5. 1, 2, 3, 4. That one's a lot closer. I'm in the ballpark there. So when I sketch my graph and then I compare my answers for x-intercepts, I'm giving myself a lot of confidence that I've done the right thing. All the pieces are fitting together very nicely. So the domain is going to be all real numbers, and once again I'll just show that using interval notation. That's all real numbers using interval notation. And then the range is all the numbers that start at -7 on the y, and then they're going to keep on going higher, or they get bigger. So here's the way we would show that in interval notation. I'm going to include -7 as part of the range, and then the numbers just keep getting bigger from there. They keep going toward positive infinity. Or in other words, using set builder notation, the range would be all y such that y is greater than or equal to -7. So these are synonymous. I just want you to get used to seeing interval notation for future reference. All right, so there's the completed answer for number 7. Then in chapter 3, we worked with imaginary numbers. So these complex numbers that are being subtracted, one subtracted from the other, it's really just a matter of combining like terms. So the real number terms, 3 minus 7, that's -4. And then -2 minus 5i, that's -7i. So the thing to keep in mind here with complex numbers is make sure you always put the real number part first, and then the imaginary part will always come in second. A complex number is a combination of real and imaginary. All right, so number 9, we're going to use the FOIL method. So the first numbers multiplied together would be 15. The outside numbers would be -18i. The middle numbers would be +20i. And then the last numbers would be -24i squared. But keep in mind, 2 things that are important with the number I. First of all, by definition, is the square root of -1. Well, if you got rid of that radical using algebra, you would square both sides. That gives you another statement that's true. I squared is equal to -1. So whenever you have I squared, it needs to be replaced with -1 to simplify. So when I replace I squared with -1, this becomes -24 times -1, which is really +24. All right, so I can combine 15 plus 24 and make 39, and then I can combine these two like terms, these imaginary numbers. -18 plus 20 is +2i. So there's my answer for number 9. Number 10, I'm going to first simplify the square root of -49, and that's 7i. Now I can multiply these together. That's 42i. But remember, complex number form means the real number comes first, so that's -9, and then that would be plus 42i. There's my answer for number 10. Number 11, remember I squared is negative 1, so you could turn this into positive 3. Negative 3 times negative 1 is 3. So 5i times 3 is 15i. It's pretty easy. For these complex numbers that have, well, we have a complex number in the denominator, the way we take care of this, the way we simplify is by using what is known as the complex conjugate. And this is the complex conjugate for 3 plus 5i, which is 3 minus 5i. So you just use the same numbers, just change the sign in between them. And distribute on the top, 4 times 3 is 12. And then 4 times negative 5i is negative 20i. And on the bottom, you could go through all 4 parts of FOIL, but you'll discover with conjugates that the outer and the inner parts of FOIL will always cancel out. They'll just make 0. So really just multiply the first 2 terms together. That's 9. And then you're going to have negative 25i squared. But again, I squared is negative 1. So that's going to make this plus 25. Okay, so the bottom becomes 9 plus 25, negative 25 times negative 1, which is 34. And then the only thing left to do is with complex numbers where fractions are involved, we want to break this up into 2 reduced fractions. All right, so I can divide 2 into both 12 and 34, so that's 6/17. And then I can divide 2 here also. This would be 10i over 17. So there's my final answer for number 12. For number 13, the best way to simplify these powers of I that are large is to remember that any multiple of 4 exponent for I, doesn't really matter what it is, any multiple of 4 exponent is equal to 1. Okay? It's like I squared times I squared. Negative 1 times negative 1 is positive 1. So what I would do is think of a multiple of 4 that's less than 27, the biggest one. That would be 24. And then multiply that, set up 2 factors so that the product would be 27 for the exponent. So remember, when you're multiplying, you add exponents together. So I to the 24th is just 1, and I to the negative third is negative I. So 1 times negative I is negative I. So that's my answer for number 13. And then number 14, you could just take these 2 at a time. 2i times negative 4i is negative 8i squared. But once again, I squared is negative 1, and negative 1 times negative 8 is 8. And then just bring down the times 6i, and you end up with 48i. Okay, so that takes care of 14. Now let's go to our Chapter 4 material. And what I would do in this problem is go ahead and combine these 2 x's and the 2 y's, because whenever like bases are being divided, we subtract exponents. So I'm going to turn these 2 different x's into just x to the first, 3 minus 2. And then these 2 y's would be negative 2 minus negative 5. That's negative 2 plus 5. That's y to the third. And then remember what negative exponents do? They say to write the reciprocal or to flip the number that's underneath. I'll just go ahead and put a 1 here. So I'm going to flip this over, and then I can change this to just regular exponent 2. And now just square everything in the parentheses. So 1 squared, 3 squared, x squared, y cubed squared. When a power gets raised to a power, that makes y to the 6. You multiply exponents in that case. So that's my answer for 15. So for 16, before you multiply, make sure you take care of exponents. So I'm going to raise everything in here to the second power. So negative 5 squared is 25. X to the second raised to the second makes x to the fourth. This makes y to the 8th. And now I can multiply these two together. So the coefficients times each other. 25 times 2 is 50. X to the 7th. When you're multiplying like bases, you add exponents. And y to the 10th. Okay, let's do a long division problem. So a minus 3 is dividing into a cubed minus 6a squared plus 10a minus 3. When you're doing long division, you really are just dividing the first term of this binomial into the first term of this polynomial. So a cubed divided by a is a squared. And then you multiply a squared times each of these. So a squared times a is a cubed. A squared times negative 3, negative 3a squared. Subtract. So the a cubes cancel. Negative 6 plus 3 is negative 3a squared. Bring down the next term and then repeat. A into negative 3a squared goes negative 3a. And then multiply negative 3a times a. And negative 3a times negative 3. All right, subtract again. A squares will cancel. 10 minus 9 is 1a. Bring down the next term, and let's divide one more time. A into a goes one time. And multiply. We have a 0 remainder. And so my answer is a squared minus 3a plus 1. Okay, 18 and 19 are composites. And these types of problems will be on your exam, so make sure you're able to do these. The way these work is you always work from the inside out. So what I mean by that is find g of 2 first. So g of 2 means I'm going to input 2 in for x in the g function and see what comes out. Okay, so 2 squared is 4. Remember to do exponents before you multiply. And 4 times negative 3 is negative 12. Now this is going to become the input for the f function. So the output from this first function becomes the input for the second. So I'm going to do input negative 12 into the f function. And that's negative 24 plus 3, and that's negative 21, and that's my final answer. It's not two answers, it's just one final answer. Okay, here's another example of composite functions. First thing we're going to do is f of negative 5. So let's input negative 5 into the f function and see what comes out. Negative 10 plus 3 is negative 7. So now negative 7 becomes an input into the g function. Okay, so do the power first. That's 49 times 3. And that's negative 3 times 49 is negative 147. Okay. For these, you should know based on functions, and there's two key parts to this function that tells what happens on the right side and what happens on the left. So we can read this first number, we call this the lead coefficient, and if it's positive, if the lead coefficient is positive, that tells me that the function has to go up on the right. So let's see, of our 4 functions here, these two, we'll just call it like this, these two, C and D, have to go up on the right because the lead coefficient is positive. So therefore these have to go down. A and B represent functions that go down on the right. Okay, then we do the left side by looking at the degree. So for letter C, the degree of this polynomial is 3. So you can remember it like this: odd degree, opposite. Okay, odd means opposite. So this one, if it goes up on the right, it has to go down on the left because it has an odd degree. So let's see, a function, a graph that goes up on the right, down on the left. Well, this one has to be C. Letter D has an even degree, so it's going to do the same thing on the left as it did on the right. So this one, we're looking for a graph that goes up on both sides, and that's going to be this one. Okay, so that just leaves these two that go down on the right, and remember, odd means opposite, so I'm looking for a function that goes down on the right but then up on the left. Well, that has to be this one, and then therefore this one has to be B. It's going to go down on both sides because it goes down based on the lead coefficient, and an even degree says it's going to match that on the other side. Okay, so finding zeros. The way we find zeros of a function is we do what is known as the rational root theorem. And so we're going to list out all the factors of this last number, constant, and then over that we're going to list out the factors of this very first number, this lead coefficient. And these become numbers that we test in synthetic division. Okay, so what I'm after here is to try to find the number out of this list that makes a zero remainder when I divide. And I'll try to save you a little bit of time. The one that makes a zero remainder out of this list is going to be -2. Okay, so what you would do typically is you just go down the list, you start trying numbers. Here's how it works with synthetic division. So I brought down my first number, multiply, -2 plus 2 is 0. Multiply again, 0, and then add. 0 plus 3 is 3. And then multiply -6. 3 times -2 is -6, plus 6 is 0. So I'm looking for 3 zeros for this solution, and one of them is -2. So the other two are going to come out of this. These numbers represent x squared, and there's no x, and then there's a constant of 3. So x squared plus 3 equals 0. And then I just solve for x equals -3, x equals plus minus I root 3. So since this really represents two different answers, one positive, one negative, then that's 2 of my solutions, or zeros, and then to go along with -2, that makes 3. Okay, so let's try this one. Once again, just start listing out the factors of that last number. So let's see, we'll have 10, 20, 25, 50, so we've got a bunch. All of those, and underneath we'll list out the factors of the first number. And once again we start testing. So we'll put, this is just synthetic division, put the coefficients and the constant across the top. And these numbers that we got out of the rational root theorem, we just start testing. Okay, so let's see, you can start with 1. 1 times 1 is 1, plus -3 is -2. -2 times 1 is -2, plus 21 is 19. 19 plus -75 is -56. Well, I can tell I'm not going to get 0 out of this. -56 plus -100 is -156. So since I didn't get 0, that means that 1 isn't one of my zeros, so I keep looking. Okay, so just to save you a little bit of time, I went ahead and I tried 1 and 2, neither one of those worked, and then I went to -1 and I got a 0 remainder, so that means I found 1 of my 4 zeros. And so what's left, these numbers represent a third degree. I divided into fourth degree, so these represent x to the third minus 4x squared plus 25 minus 100 equals 0. So I'm going to go through the table process again using those same factors, but there's a little trick that if you recognize it, it really comes in handy. When you're at third degree and these coefficients multiply together to equal the constant, 1 times -4 times 25 equals -100, then that tells you that the 0 that you're looking for will be the opposite of whatever's in front of x squared. So that makes hunting through the list a lot quicker. So let's see if that works. 4 plus -4 is 0. 0 plus 25 is 25. 100 plus -100 is 0. So there's my second 0. And now I've got 2 found. I've got 2 more to go. So these numbers represent x squared plus 25 equals 0. Solve this. And my other 2 zeros are positive 5i and negative 5i. So there's my final answer for number 25. All right, 26, find the inverse of each function. So the way I find the inverse of a function is I switch places with x and y. So treat this as y. So switch x and y, and then solve for y. X plus 6 is 5y, and I'm going to multiply by 1/5. And instead of y, since this is the inverse, when I've got y solved for and I'm trying to find the inverse, I'm going to use the notation. Since this was called f of x, this is called the inverse of f of x. All right, and then the directions say to graph the function and its inverse. So here's the graph of the function. It's just y equals mx plus b. So it has a y-intercept of -6 and a slope of 5. Okay, so you would, I'll try to draw a straight line. You just line those points up and draw a line through them. And to get the graph of the inverse, you could graph the inverse function that we came up with, or you could switch the ordered pairs on this. So for example, this is 0, -6, so you can plot -6, 0. This is 1, -1, so you can plot -1, 1. This is 2, 4, so you can plot 4, 2. And this line, I'll just label them. This is f of x. This is the inverse of f of x. Okay, here's a parabola. So let's do the same thing here. Let's find the inverse. So switch places with x and y. And then solve for y. So I would subtract 3. I'll do the square root of both sides. And then I'll subtract 2. And this is the inverse. All right, so now let's do the graphs. So this is a parabola. The vertex is at -2, 3. Remember, this is called vertex form. And you can do some other inputs to get the rest of the parabola, like input -1. -1 plus 2 is 1. 1 squared is still 1. So that would be -1, 4. And because of symmetry, we have that other point matching it. 0 would give me 7. 2 squared is 4, plus 3 is 7. It's right there. And because of symmetry, I have a matching point. So there's the graph of f of x. That's the point, but I think you see it. Now let's graph the inverse. We'll just do this one in red. So just take these ordered pairs. This might be a little complicated for some people to graph, but you can always just take the ordered pairs and switch the coordinates. So take -2, 3, switch the xy coordinates, and you have 3, -2. Take -1, 4, and 4, -1. This is 1, 2, 3, 4, negative 4, 7, so do 7, negative 4. This is 0, negative 7, so do negative 7, 0. And the other one is right here, 4, negative 3. So the red represents the inverse. We'll label it. And that's it. There's the way to come up with the inverse function, the graph of the original function, and the graph of its inverse. And we just have 2 more, and we'll be done with this. So here's some radical equations, and the way we solve these radical equations is first isolate the radical. So my first move is to subtract 4 from both sides. Then this is a square root, so I'm going to raise both sides to the 2nd power. And that gets rid of the radical. I add 1 to both sides. I divide by 3 on both sides, and so my answer for number 28 is 17/3. So once again, isolate the radical. Raising something to a fraction is another way of saying radical. So let's do the 2 steps needed to isolate the radical part. We're going to add 6. Then we're going to divide by 3 on both sides. And the way I undo raising this to the 1/3 power is I raise it to the 3rd power. 3x minus 1 is equal to 8. 3x is equal to 9. X is equal to 3. And that does it. That concludes our review of some Chapter 1 topics to try to get you ready for some of the Chapter 1 material that will appear on the Semester 2 exam. I hope this helps in your preparation. If you have any questions, let me know.